Who is ELEK Software? Well, we are a software company based in Sydney, Australia. Most of our technical team is based in Sydney, but we're also a distributed team. We have three main software products: ELEK Cable Pro Web on the left-hand side, ELEK Safe Grid Earthing Software, specialized earthing design software, and ELEK Cable High Voltage Software for cable rating calculations. Along the bottom, you can see that we have a very high number of high-profile customers that are using our software. We've been developing software, leading software since 2009, with tens of thousands of users in many, many countries. ELEK Cable HV software was used for the modeling where necessary in this presentation. You can see along the top of the screen, it provides a lot of capability in terms of calculations. So it's accurate and validated software for cable current rating calculations. It's suitable for any AC voltage, including low voltage up to any AC voltage and any DC voltage, including HVDC. Complies with IEC 60287, but also can perform the finite element method calculations in a very easy way. Those calculations are not easy to configure, but we make it very, very easy with our software. So you can perform current rating calculations for your custom cables from manufacturer data sheets under your specific conditions. As I mentioned, the accuracy of the calculations has been fully validated. You can download, actually, you don't need to download. If you go to elek.com, you can register for a free trial. You don't need to download it. You can use it immediately on the web. Within 2 minutes, you can be using it. And it's fully functioning. So the contents of this presentation, it's a purely technical presentation. There is a live software demonstration towards the end. Horizontal directional drilling fundamentals, particularly focusing on cable systems. I'll talk briefly about the differences between traditional HDD and HDD for cable systems. There is a big difference. HDD profile design and cable configurations, there are a few options there. Duct, pipe, sizing, material selection, and filling materials, and the effects on cable ampacity, of course. The maximum depth and length limitations for cable systems in HDD. Cable pulling forces with an example calculation, also an important factor. Soil resistivity, possibly the most important factor. And when you're dealing with multiple soil layers for deep HDD. How to model HDD cable installations properly. Then we will lead into some calculation examples. A live software demo. Edston will take over. We'll ask him some questions. We'll look at shallow HDD that is near emerging from the ground surface that may be air-filled. We'll look at a point in the HDD installation that is just above the water table where soil dryout may occur. And we will look at the deepest point of the HDD installation, which is, in this case, bentonite filled. And we'll talk about whether, what's the hotspot, what's the dictating installation condition with regards to the ampacity of the cables. We'll draw some conclusions and recommendations. There will be a live Q&A session. And as Edston alluded to, if you stick around till the end, we will give you a link where you can fill out a form and request a certificate of attendance, perhaps for CPD points. So what is horizontal directional drilling? There's some images on this slide in the top right-hand corner of the process. So it's a trenchless method for utilities, traditionally for gas pipelines, water lines, sewer lines, and also cable systems, but with some key differences, especially for cable systems. So with cable systems installed in HDD, there are some depth or thermal constraints that we need to consider that are quite limiting, and length limits in terms of cable pulling as well. But the method enables river crossings, road crossings, or crossings under developed areas. Generally, it involves three stages. So you can see in the images, the three images there. So there's a pilot bore, there's a reaming, so that's enlarging the bore. That's the second stage. And then there's the pullback of either the pipe or the cables or ducts or both or all. The equipment involved is usually a drilling rig, drilling bits and rods, guidance systems, drilling fluids, slurry pumps, and reaming and pulling machines for the cables and the ducts or pipes. Cable ampacity is quite complicated. It depends on the depth of the HDD, the cable type, of course, the cable specifications, bonding, the ducts, materials, dimensions of the ducts, how many layers of the ducts, whether it's ducts inside a pipe or not, what the ducts are filled with. Then there's the native soil thermal resistivity, and there's the soil ambient temperature, also a very important factor. So that's HDD for cable systems. And you can see in the bottom right-hand corner, you've got some images of the actual drilling process and then even the cable pulling process as well. If you have any questions along the way, please type them in the chat. HDD profile design. The bore path creates a horizontal path. You can see along the bottom, we've got a diagram. For PE pipes or ducts, the safe long-term deflection is 7.5% of the diameter. So the angles of this drilling installation should be limited. Of course, for the pipes or the ducts, but also, of course, for the cables. So the bending radius of the cables. Some PE pipe manufacturers recommend an allowable bend radius to diameter ratio of 40 to 50 times during installation. So these sort of rules you should follow or at least consider in your HDD installation designs. The borehole is enlarged by reaming and then pullback of pipe or cables we saw on the previous slide. Now, the drill fluid slurry surrounds the pipe, effectively filling the gap between the pipe and the bore cavity. So what happens after we pull in the pipe? Are there air gaps between the pipe and the native soil after the drilling? Probably not. And if there were, that could be a thermal hotspot because air actually has a high thermal resistivity. But it's generally regarded, this is quite a wet process. And the slurry that's produced, once the pipes or the ducts are pulled into the bore, the slurry generally surrounds and is in good contact with the pipes or the ducts. So it's a good thermal situation. So what are the HDD cable configurations? There are a number of them. I'd love to hear what your experience is in chat. Which option do you mostly see when you're dealing with HDD cable installations? But for me, it's options 1. I've seen 1 to 3, but I haven't really seen 4. So in general, the casing pipe provides additional cable protection. So that's option 1 or 2. So let's talk about option 1. So that's where we have installed a larger casing or a pipe into the borehole, and we've pulled ducts into the borehole, and then we've installed cables inside the ducts. It provides very good protection and allows easy retrieval of the cables. That's the advantage being inside the ducts. These pipes and ducts are generally filled with bentonite, and we'll discuss that a bit later. Option 2 is without ducts inside the pipe. It's less common. the pipe still protects the cables. The pipe could be different materials. Usually it's HDPE, plastic, and it's generally a cost consideration. Uh, but also option three is an option and where the borehole size is limited and providing individual ducts does allow individual retrieval of the cables, which is an advantage. And then you have option four where the cables are directly installed inside the borehole. This is, in my view, not recommended. There's damage to the cables could easily occur. However, where cost consideration is high or limitations are high, and where additional spacing is required for thermal reasons, mutual heating between the cables, if you need to provide that, then option four could possibly be used. But what's your experience in the chat? We'd love to know. What have you mostly seen?
Mostly option one, many of them.
Mostly option one. I think that's what we
Yeah.
had in the last
Yeah.
installment. Yeah.
Yeah.
Any other options that you're seeing there, Edston?
Option three.
Option three. Okay. Yep.
Yeah. Separator faults. Yeah.
Makes
That's
sense. Makes sense.
yeah. Yeah.
Okay. So is there a delay in my slides or not?
No,
Not
it's all good. It's
okay.
good.
HCD pipe or duct material and sizing. So we need to use materials compatible with cable operating temperatures. So we're talking about, so if we have a conductor temperature of 90 degrees Edston, what would we expect for the outside sheath or jacket of the
Uh,
cable?
Mostly depends on the soil, but we have seen anywhere between 50 degrees to 60 degrees
50
for the
degrees or
jacket if
60
it's
degrees for
directly
the
buried.
jacket of
Yeah.
the cable.
Yeah.
Yeah, yeah. So we need to use materials of ducts and pipes that can tolerate those sort of continuous temperatures. HDPE is generally used and preferred for HDD installations, and we recommend you join the sections using butt fusion method for good strength. Where higher strength is required, you could use a steel pipe. What's the problem with using a steel pipe, or some problems with using steel pipe, Edston?
Yeah. Mostly because of losses.
Mm-hmm.
Uh, yeah. We would have some like armor losses. We would have something similar to that on a steel pipe.
Yeah, so
Yeah.
circulating like eddy current losses in
Eddy
the
current losses. Yeah.
steel
Yeah.
pipe, right?
And hysteresis losses also
And hysteresis
on
losses
yeah
if it's magnetic steel, right?
magnetic steel pipe. Yeah.
Yeah, yeah. So you could use stainless steel, which is non-magnetic, which avoids magnetic losses, and it has increased corrosion protection. But of course, steel pipes are much more costly um, and difficult to handle and weld, of course. So let's talk about the sizing of these pipes. The inner diameter must exceed the cable and the pulling assembly. Uh, so that's going to be larger than the cable diameter itself. Typically 1.5 to 2.5 times their overall diameter. That's a general rule. Typical sizes we see for pipes are between 200 to millimeters to 1.8 meters. And ducts inside pipes, generally, if you're talking about option one, you generally would see 200 millimeter to 300 millimeter inner diameter pipes, ducts, sorry, being used. But you'll need to allow for extra space inside the ducts to allow grout to flow and be installed uh, in in the full length of the duct. So here's a bit of a guidance on HDPE pipe dimensions. There is a table here. It's probably a good idea to take a screenshot of this slide. You can obtain these dimensions of different HDPE ducts from manufacturers, but not that easy to get. So there's some guidance here about sizing your pipe or your duct when there are multiple cables inside or ducts inside the same pipe. If they are the same size, you can use these multipliers here. So it's then if I had three ducts of the same size and I needed to pull them inside the pipe, then I could use this multiplying factor, right?
Yes. Yeah. So if it's three pipes, the minimum is 2.16 multiplied by the cable or the duct diameter, and that's the
Yeah.
minimum value. Yeah.
So that's the minimum inner. So if I had ducts, three ducts, and I wanted to pull them inside a pipe, and those ducts had an outer radius of 200 millimeters, then the minimum inner radius for my pipe would be 2.16 times 200, right?
Yeah. Yeah. Or we can just
And
table. Yeah.
that's the absolute minimum. And then duct selection. This table is about selecting, standard duct sizes of particular strengths or SDR ratings, right? And there's a note here that the recommended SDR for HDD is SDR 21 or less. Okay, so this table here starts at 21 and goes to less, obviously. So an SDR, a lower SDR will have higher wall thickness and obviously cost you more and be more difficult to deal with. But that's something that you need to weigh up. Maximum depth of HDD cable systems, there is a limitation, and that's mostly because of the thermal limitations related to ampacity. So it's critical to determine the maximum depth of the HDD cable system because cable ampacity is directly proportional or related to depth, right? So the deeper the cables are, the hotter they get, and their ampacity ratings suffer. So typical depths for HDD cable system installations, you'll see between 10 to 30 meters. That's maximum depth, where you're balancing structural stability with thermal performance and, of course, constructability. The good news is that at high depths, that soil temperature is relatively constant and it's also lower than at shallow depths. So soil temperature is lower, which can lead to ampacity improvements, right, compared to at the surface. So as I mentioned, the greater the burial depth, this increases the thermal resistance experienced by the cable, leading to higher ampacity derating. The images here in the bottom left-hand corner, you'll see a cross-section of a real HDD installation or a bore. And actually on the bottom right-hand corner, you'll see real temperature measurements of a cable installation after the fact. And you'll notice that the highest temperatures of the cable are not necessarily at the deepest point. In this case, there is a hot spot that's developed in the shallow section. And actually, the reason for that is so this HDD was filled with bentonite, and that shallow section, there was an air gap, essentially air gap. It wasn't properly filled with bentonite at the end. The higher end, the end with at the higher elevation, an air gap developed, causing a hotspot, and you can see that the optical fiber has measured that hotspot. So it's not always the deepest point. So this is a plot of a real HDD cable system with a pipe surrounding four ducts and the cables installed in three of the ducts. It's essentially there's a spare duct. And you'll see that as we vary depth of burial, or the HDD is buried from 5 meters to 30 meters, that cable ampacity varies significantly, between 490 amps and low 400 amps, just from the burial depth. And there's these two images in the right-hand side. There is an FEM, finite element method mesh plot. Actually, to do these calculations properly, you need to use the finite element method. We will explain that there are some simple analytical methods to kind of do it, but there's some assumptions. And then you can see a temperature plot here of the isotherms surrounding the HDD following the ampacity calculation using FEM. If you have any questions about this, feel free to put them in the chat. I'm sure Edson can answer them. HDD cable length limitations. The main limiting factors are tensile strength of the cable. There's a maximum allowable pulling force of the cable, as we should know. The reel length, you cannot pull a cable longer than the length of the cable on the reel. And cable splicing or joints are not possible to pass through or into the joint, into the HDD. So typically, most HDD installations are limited to around 1,200 meters in length. But what's your experience? We'd love to know. Please type it in the chat. I think everyone would love to know what's your experience. What typical lengths have you installed HDD cable systems? There are many shorter HDD cable installations, of up to a couple of 100 meters is typical in what I've seen and in the literature. And the longest HDD installation that I'm aware of is a cable project which is around 2,000 meters in length. That's from a 2023 reference. But if you have some other experience, please type it in the chat. Everyone would love to know. So cable pulling forces, we need to calculate them. The peak tensile pulling force must be compared with the allowable stress limit of the cable. And all cables have a maximum allowable pulling force. And sometimes it's easy to get, sometimes it's not. Sometimes it's right at the back of the catalog. You can calculate it. It's not recommended. I recommend that you get the maximum allowable pulling force from the cable manufacturer directly, and you're clear about that limit. So the interior pipe and duct surfaces should be pre-lubricated. And when you're doing these calculations, you'll need to use or assume a value of the coefficient of friction. So also when you're pulling into a borehole, there'll be quite a lot of drilling fluid and mud slurry. So if you're pulling cables or ducts into the bore, and you want to calculate tensions, you can do that. We would recommend a coefficient of friction of 0.3 or thereabouts, not lower than that. And when you're pulling cables or ducts into a pipe or cables into a duct, depending on the lubrication method and various other assumptions, we recommend a coefficient of friction of between 0.35 and 0.7. You can perform these. We provide cable pulling tension calculators on our website. You can just go to elek.com or Google them, you'll find them. So in the photograph here, you'll see 3 ducts being pulled into a pipe in one pull. Here's an example cable pulling force calculation, which I'll explain. So we ran the calculations for 3, what was it? It's 110 kV cables.
132 kV. 132 kV.
What's the
kV, yeah.
conductor size on these?
630 mm squared.
630 millimeters squared conductors. So pulling those three cables in at once into a single pipe. Can be any other arrangement, but this just gives you an idea of the calculation. So forget the drilling machine on the left-hand side. On the right-hand side, you've got some pulling happening. The direction of pull is from left to right. There should be a drum where the drilling machine is actually. And you see that, so those numbers there, 497. So starting from the left, after the first section, you've got a slope down of whatever angle it is. You can put it into the calculation. So 20 meters slope down may or may not be really realistic, but 497 at the end of that slope down, you've got 497 newtons, which is really not much to pull. And it's not much tension on the cables. So these cables each have a maximum pulling tension, allowable pulling tension of, I think, is it 85 kilonewtons, Edston, something around that?
Yeah, it is 85, yeah.
Around 85
Around
kilonewtons
85, yeah.
each. Now, when you pull three of them at the same time, they support each other. So in effect, it's more than 250 odd kilonewtons. However, we should apply a factor, right, Edston?
Yeah, we should have a reduction factor for it.
A reduction factor
Reduction factor, yeah.
and what's the reason for that?
Because the cable friction is a bit reduced. And those cables support each other.
Uh-huh. Uh-huh.
Yeah, but it's not too much of a reduction. It's that 5% or 6%, maximum is 10% what we normally use.
Uh-huh. Okay. Yeah, so we don't have much tension after the first downward slope, and that's because the cables are actually more or less falling in the first section. So gravity is supporting the pull in the first section, and then we have a long, in this case, hypothetical 1 kilometer horizontal section of HDD. It wouldn't be so ideal like this, but tension significantly rises. Now that 233 kilonewtons, that would be the tension at the end of the 1,000 meters. So that's the tension that's accumulated. And then we have the last section, the rise, the inclination going up, and we add another 7, 8 kilonewtons to the pulling tension. Now we need to make sure that the total pulling tension doesn't exceed the limit for the cables, or else we can't proceed with the pull. Soil thermal resistivity. Soil provides the largest thermal resistance and capacitance in HDD cable systems. It's not just HDD, but any buried cable. It's an extremely important factor in cable thermal analysis, cable ampacity. Cable thermal resistivity mainly depends on the soil type, the moisture content, and the density compaction of the soil. Designers must obtain in situ soil thermal resistivity for accurate cable ampacity calculations. Soil dryout behavior and long-term stability should be verified during the geotech survey. So this photograph is not really what you would expect for a soil thermal resistivity survey for a HDD. It would actually involve boring and sampling. It wouldn't be a guy climbing into a hole. This is typically for another sort of standard buried installation application where you're taking samples like this. But it would be bores and samples, drilling down as deep as your HDD, and then taking samples. You should offset your boreholes from your drilling path. They shouldn't be in the same path. But it's very important to obtain these values, these measurements. Now with HDD, because we're drilling so deeply, there could definitely be layers of different thermal resistivity. This is where I'll call upon Edston's expertise to explain some of this, but I'll explain some of the fundamentals. So these HDD routes often cross layered soils with different resistivities. We should consider this. So in general, poor layers can create hotspots and derate cable ampacity, and good layers, meaning low thermal resistivity, can shed heat, especially longitudinally. Fluid-filled ducts can enhance longitudinal heat transfer along the conduit. So when we are having different thermal resistivity, layers of different thermal resistivity, we should start to consider not just the radial heat transfer, but the longitudinal heat transfer along the cables, along the ducts, etc. And so in general, when you have this situation, rating calculations should include both the radial and longitudinal heat transfer or heat flow. And radial alone may not be sufficient. So let's talk about this technique. Now, I was discussing this with Edston in the last presentation, but there's two ways of dealing with this. There's FEM, and then there's this conformal mapping, which is like an analytical technique, right, Edston?
Yes. So normally when the HDD passes through different soil thermal resistivities, we prefer FEM because that's more accurate.
Yeah.
But if FEM is difficult to model, then we can use a technique called as conformal mapping, which can be used in conjunction with the IEC methods, and then we can continue using the IEC methods and conformal mapping together to get
So the IEC methods
ratings. Yeah.
for standard buried cables, right?
Yes.
Can you
Yes.
explain these images here? So starting
Um,
from the left.
Yeah, so I think the image on the far right, which shows the concentric circles, is what is the IEC method, which uses Kennelly's hypothesis and a
But we wouldn't have so
isothermal
many
ground
circles,
surface.
right?
Uh,
The multi-layers introduce the multiple circles. Is that's right?
Not exactly, because these
Okay.
would be contours of the circles of the temperature profile. For example, even if you consider single layered soil, you would have contours of circles.
Oh, this is
But
temperature.
yeah, temperature profiles. This is showing the Kennelly hypothesis. But
Uh-huh.
if you try to do this with a multi-layered soil, what we can do is we can transform this into a new plane, like a Laplacian transformation, which can turn this circular contours into parallel contours. So that will make analysis pretty easy with cables having different depths in. So you can in this figure you can have cables in different depths, and then you can get an equivalent thermal resistivity for a cable in that particular layer of soil.
Yeah, yeah,
So
yeah.
that's what the second image shows.
Uh-huh. So we'll talk about this example, but before we do, there are some basic approaches you could take, right? If you have a HD installation, you know that there are multiple layers, right?
Yeah.
There's a couple of basic approaches that you could use, right? So what are they?
Yeah. Normally, what we have seen everyone using is assuming that the soil with the worst thermal resistivity being the hottest point. So if 1.5 is the worst thermal resistivity, everyone assumes that to be the worst condition, and assume
So if
that
you
to
have
be a
multiple
uniform soil.
layers and
Yeah.
1.5 is the worst, then
Yes.
effectively use 1.5 for all depths,
For
right?
all depths, yes, that's
Uh-huh.
one thing. Some people assume that the deepest point of the cable installation would be the hottest point. So, for example, in this case, we have a cable starting from the ground surface going up to a maximum of 12 meters. So, 12
In this
meters can be a
example, right?
point.
In this
Yeah, in this
example, right?
example, yeah, 12 meters. So we could say that 12 meters is a point where might be the hottest point. But we've done some studies, and these plots show that that may not be the case always. Uh, so the first plot on the top on the right hand
What are
side,
these? So these plots, these are plotting T4, which is external thermal resistance of the cable, which is directly rated to heating of the cable, right?
heating of the cable. Yeah, we do this method because we can integrate this directly with IEC 60287, and the
Yeah.
T force would be calculated using this method when you're traveling through different layers of soil. So if you plot the T force with the depth of installation, you would see that the middle layer, which is around I would say 3 meters depth of that layer, is there where we get the hottest spot. But if we
So the top right hand plot if you go from depth, so from shallow depth, you see that
Yeah,
and you start in the top layer and
yeah,
you arrive in the middle layer, then the cable temperature would be hotter in the
yes.
middle
In the
layer at
middle
that
layer,
depth at
yes,
around 6 meters. Then when
yes.
you go past that into the lower resistivity
Lower
layer,
series, yeah,
you'll get a lower temperature, right?
lower temperature. Yeah, yeah. That's what
Now,
this
the
shows. Yeah.
bottom right-hand plot, I think the labels are wrong, right? The
Yeah,
blue and the
labels are wrong.
green.
The first label should be 1.5, second label should be 1.
Ah.
Yeah, so in this layer we would see that the shallowest portion is one where we have hottest point, not considering salt dryout in this case,
But
but without, yeah,
in both those cases, though, if the bottom right-hand corner, the blue color is supposed to be 1.5 and the green is supposed to be 1,
yeah.
then we're seeing the hottest points inside the highest soil with the highest thermal resistivity, right?
Yeah, that's because of this installation. It's depending on the installation and where the cable, how the cable passes through it. So I mean, like if these values were different, or if the thicknesses of the layers were different, we would see a different result completely.
So we can't really predict it. Is that what you're
Yes,
saying?
yes, we can't really predict whether the highest thermal resistivity would be the hottest point, or the
Yeah.
deepest point would be the hottest point.
Yeah, yeah, yeah.
So yeah, so that's why. So FEM will be the best, but if not available, then the conformal mapping would be good. It's a less bit accurate, less accurate compared to FEM, but easy to calculate, easy to integrate with the IEC methods also.
And what's the story of the bottom left-hand corner, those numbers down
Yeah,
there?
so this cable was assumed to go to be installed at different depths. For example, we consider 2,500 millimeters, 6.5 meters, and then finally 12,000 meters. So they show you the T4 calculations at each of these depths. And if you consider that they have inclined with the horizontal at an angle of 20 degrees, you would see a new T4 value, or an modified T4 value because of the inclination. So the
So
inclination
in all cases, we see that there's a higher T4 when the ducts have a slope, right?
have a slope. Yes, yes,
So ducts that are well, sections of HCD that are sloping
yeah.
uh, would most likely be hotter
Be
than
hotter. Yes,
sections that are horizontal.
yes, yes, yes.
Yeah. But you mentioned earlier today that although it looks like a significant difference in T4, in terms of ampacity, it's not that much, right?
Yeah, I mean, if you look at it, it's 0.48 and 0.51. Not
Yeah.
much of a difference there. And the last layer, even at 12 meters, you have only 0.44 and 0.47, which doesn't make much of a difference in ampacity. But if you change the angles, if you increase the angles, you might see a bit more of a
If you
difference in
increase the
T4s.
angles
Yeah,
further,
yeah,
you might
for
even see
yeah.
more of a difference. Yeah.
Yes,
Yeah.
yes.
Got it. Interesting. So let's talk about soil temperature. Um, Very important as well as soil thermal resistivity. Soil temperature varies with HCD burial depth. Yeah, soil temperature is not constant. It's generally, depending on the season, can be hotter. It's very seasonal in the shallow depths of the soil. It follows the ambient temperatures. But the good news is that you can calculate it. This is a useful equation. You should definitely take a screenshot of this. You can put this in Excel. Very easy to use in Excel, and you can actually calculate soil temperature with depth. Now, why is that useful? Because we often make assumptions about soil temperature when we do cable ampacity calculations that are very conservative, especially when you're dealing with HDD. Now, the deeper we bury the HDD, the hotter the cables get, and we derate the cables. But what if we knew that the soil temperature down in those depths was quite a bit lower than at the ground surface? So we can offset the derating of the depth by calculating the soil temperature. And this is a simple equation that you can use to do that. We have this calculation inbuilt as a calculator into our software, exactly this equation. So let's examine that. Here is a plot of soil temperature with depth. So if you look at the summer curve or the winter curve, so I think this is like a cold climate. Um, Now, so you can see quite a variation at shallow depth on the left-hand side, that's shallow depth. You'll see that there's large swings in soil temperature with the seasons. Yeah, it could be quite warm, the soil temperature, or it could be quite, it can all even freeze. But HDD installations are usually very deep. And so depending on the soil properties and the location, look, in general, the soil temperature at high depth generally approaches the annual average temperature of the location. Now, if you're in a highly tropical area near the equator where the ambient temperature, air temperature almost never varies, this won't help you. But if you're anywhere else in the world, um, the soil temperature at depth will approach the average annual air temperature, and that could be significantly lower than your usual assumption of 25 degrees, right, for your soil temperature. Way too conservative, or even 15 degrees. Maybe the average annual temperature where you are in Europe is closer to just above zero. Soil drying around HDD pipes. Soil drying is a real significant problem with buried cable installations. So the heat from the cables may cause soil moisture migration away from the pipe in this case, or the casing or the duct, or even the cable that's buried. And it causes a temperature gradient can be caused, and a dry soil zone may develop around the pipes. The good news is that these casings or pipes don't get as hot as the cable surface themselves, not even close. So as Edston said, if the conductor's operating at 90 degrees, you might expect 50 to 60 degrees for the cable outer jacket temperature. Then you've got another reduced temperature for the duct outer temperature. And then if there's a pipe as well, you wouldn't see much of a temperature increase in general for these HDD installations. That's the good news, but soil dryout is definitely seen as a problem with these installations. Don't get me wrong on that. Now, when soil dryout occurs around a pipe of a HDD or any cable, there is this sharp transition in soil thermal resistivity where it goes from low thermal resistivity to quite a high thermal resistivity. The design of a HDD installation must consider the possibility of soil dryout at the external surface of the pipe. With our FEM calculations, you just simply turn it on. And if the soil temperature at any location exceeds the critical temperature, which you define, then soil dryout is assumed and considered and will derate the cable. A practical situation in the bottom right-hand corner of this slide is where you've got the section of the HDD that is above the water table. So soil dryout is not a problem when the soil is continuously wet, like below the water table. But above that, so the deepest point of HDD, just above the water table, can be a significant risk to experiencing soil dryouts. Here's an example of where we are looking at the two factors that I've just discussed, which is soil ambient temperature and the effect of that on cable ampacity for HDD, and soil dryout. So if you look at the red curve on the left-hand side, without soil dryout, you can see the effect of soil ambient temperature. So 25 degrees compared to 5 degrees, you've got quite a large difference in ampacity, around 100 amps. So suppose that you needed to assume 25 degrees for your HDD for soil temperature. You're going to lose, 100 amperes in the installation if you make that assumption. However, if you calculate soil temperature and you work out that for your deep burial is section of your HDD that it's more like 5 degrees or 10 degrees, or you can potentially get another 100 amps out of the installation, right? Now, when you add soil dry out to the equation, you see a significant drop in cable ampacity. So that's the blue curve. So if the soil dries out and then there's variation in ambient temperature, that's what the blue plot on the left-hand side shows. On the right-hand side, what is this showing? There's an onset
Uh,
of soil drying, right? Or
yeah, so
what's the
this
scenario?
yeah, so this scenario is we used a fixed current on the cable,
Uh-huh.
around 530 amps,
Mm-hmm.
and we changed the ambient temperature with and without soil dryout, and then
Uh-huh.
we
Uh-huh.
found out what is going to be the temperature of the conductor. So
So
these numbers show you the temperature. Yeah,
constant current. So
yeah,
when we change the environment, so we're just varying the environment, which is the ambient soil temperature
yes,
experienced. And then once you exceed a certain ambient temperature, I guess the outside temperature of the pipe exceeds the critical temperature for soil dry out. And then
yeah,
you get this jump, you get this reduction
reduction. Yeah,
in
yeah, in ampacity
cable
or
ampacity, right?
yes, yes. Yes, because when the ambient is because what we have used is a 40-degree drop
Sorry,
temperature.
there's a jump here in conductor temperature,
Yeah, so
which is in blue
drop.
when soil dry out comes, right?
Yeah, yeah, and that's what
Carrying
the
the
drop
same
in
current.
kind
Yeah.
of the same current. Yeah, yeah, yeah. Yeah, so because we are using a 40-degree dry out temperature, which is, for example, if the ambient is 5, 40 is pretty far away, and the soil dry out may not occur at that point with this temperature because the maximum temperature is only 48. So dry out occurs, but doesn't occur that much. But as you increase the ambient temperature, the conductor temperature also increases, and that induces more of a dry out of the soil. That's why we see that jump after about 15 amperes, or sorry, 15 degrees. We see that jump there.
Mm-hmm. Cool, cool. Okay, thanks. Filling materials inside ducts and pipes is very common to install filling materials inside HCDs. It's multi-purpose. So the thermal grout provides high thermal conductivity, of course, for efficient heat transfer. So air is a poor thermal conductor. It's more of an insulator. These grouts have good thermal properties, or that's what they're designed to do. They also provide support and stability to prevent cable movement and potentially cable damage. They protect from moisture, soil, and contaminants affecting or damaging, reducing the lifespan of the cables. And they effectively reduce or minimize mechanical stress and groundwater ingress on the cables as well. Adding grout to the cables improves performance, but it adds a cost and complexity, and you need to allow provide larger ducts to allow space for installing these materials. Yeah, so it affects the bore size, not only, of course, duct size, bore size, duct grade, um, and there is a coordination or negotiation happening between, the designers of these grout materials and usually undertaken by the drilling company and often the electrical engineers who need to know about the thermal properties for their cable designs. Air convection, air can occur in ducts or in pipes, and when it does, it needs to be modeled properly or considered. it's much more complex than considering like a solid material like bentonite. There is convection, which actually depends on the position of the cable in the inside the pipe or the duct, how the air behaves. There is convection, there's radiation, all those thermal behaviors which are more complex to examine. There are simple IEC analytical equations that you can consider. Air convection inside ducts or pipes. I think only a single duct, right? It's done, and there's some limitations, right, with IEC.
Yes, yes. For so I see the limitations with the materials that you can use for the duct.
Uh-huh.
That's because there are constants for the convection models inside the duct. So there are restrictions to the now to the duct material. There's
Yeah.
also restrictions on the size. That is like the IEC specifies that the range is about 25 millimeters to 100 millimeters, the duct size.
So duct size
Um,
is limited between those dimensions, which is very, very limiting and not really applicable to HDD, right?
Yes, and there's another major assumption is the positions of the cable. It's like in the center of the duct, which
It's
is
always assumed to be
impossible
in
if
the
it's an
center.
air-filled duct. Yeah,
Yeah, yeah,
if it's
yeah,
an
yeah.
air-filled duct, it's
Impossible.
impossible to have that. Yeah,
Yeah, yeah. So, but FEM can deal with this, right? FEM can deal with all
yeah.
these
FEN can deal with all these. Yeah, yeah,
issues.
all these
There's
issues.
no
Yeah,
dark side limitations and any
no
positions. Yeah.
positions on materials. There is nothing. Yeah.
Also, I think IEC can only deal with what, one circuit or one cable inside the duct, right? Potentially, right?
IEC, yeah, IEC can do that, but then the C grade document has methods where we can implement multiple conductors or multiple cables in a duct,
Uh-huh.
so we
Got it,
can
got it.
extend that one. Yeah,
We have that, right?
yeah, we have that. We had it already. Yeah.
Yeah. So here's an example of the effects of the filling material on the cable ampacity. You can see in the images here. So starting on the left-hand side, we've got a pipe, and the pipe is actually filled with grout. It doesn't have to be, I mean, in the model, but we've just assumed that the pipe is filled with grout. But the ducts themselves are filled with air. There are four ducts here. Three of them contain cables, single core cables, and one duct is a spare and it's air-filled in all cases. So the cable ampacity of the air-filled installation is around 800 amps. Then in the middle situation, we've got the same HDD pipe and ducts, but the ducts themselves are filled with bentonite or grout, and the cable ampacity has risen by 60 amperes. And then on the right-hand side, you've got the same ducts filled with water, which is a practical situation. It can occur, and turns out that water has the best thermal properties in this case when you're comparing it with typical bentonite, right?
Yes. Yeah.
So how do we model HCD duct-in ducts systems? When we're talking about HDD, duct in duct, or casings, cables in casings, we're talking about a pipe and ducts inside the pipe and cables inside the ducts. As everyone alluded to, that is the most common situation. It turns out that it's the most difficult, one of the most difficult cable ampacity calculation problems that exists when you have ducts inside ducts or ducts inside pipes. The thermal problem is very complicated. There are some extensions to the analytical IEC methods that can deal with some basic symmetrical configurations of this uh, with lots of assumptions and conservative assumptions that will result in conservative results. However, the image that you see here, which is from our software, that you can't model this using analytical expressions that we're aware of. Uh, and you need to use FEM. As you can see, the temperature distribution shown by the colors is um, not really uniform. And this is an overlay of a mesh plot, which is the backbone of the FEM calculations with the temperature plot. Now, FEM, the finite element technique, is very good at calculating temperatures at any locations, even inside the cables. So in general, if you want to model HCD, you need to use the finite element method. So multiple casing calculations, when we're talking about how we do them, the capabilities of these calculations, they can deal with steady state and transient calculations. Unequally loaded calculations are typical for cables and casings. Modeling capabilities, this is more or less what we have in our calculation capabilities. Any number of casings in the same installation. So actually, I think what this is showing here is two different types of casings side by side, right? If that were ever a thing. But with FEM, you can do that. You can have casings next to casings and all sorts of things. There's not really any limitation. Any number of ducts inside one or more casings. Actually, with FEM, and we've tested this, we can do ducts inside ducts inside ducts inside pipes. There's no limitation. FEM doesn't have this, but analytically, it's really, really quite difficult. Yeah, any number of circuits inside a casing. So that could also be a problem. I think in solar installations, you'll see lots of multiple circuits inside the same duct or pipe. So we have that capability. But it's another type of thermal problem. That's only in FEM, right, Edston?
Yes,
Multiple
yes,
circuits
because
inside the same duct?
yes, multiple circuits inside that can be done only in FEM.
Yeah, yeah.
Yeah, even
Multi
multiple casings also. Even multiple casings
yeah,
can also be in FEM only. Yeah.
yeah, yeah. Multiple cable types. This is also very useful with FEM that you may be dealing with different cable types in the HCD installation and different materials. You may be dealing with different duct materials, pipe materials, concrete, metal, custom materials, etc. And importantly, the casings or the pipes could be air-filled, water-filled, or solid-filled, or a combination. And there can be spare empty ducts. There could be a spare air-filled duct. FEM can deal with this. Here's just a sort of a wild installation that we've seen with lots and lots of circuits inside a massive pipe. FEM can do this. So I'll hand it over to Edston, who will show you some modeling of a HDD installations inside software. Then we will go to a Q&A session. Hopefully Edston's been able to answer some of your questions. But we'll have a live Q&A. Then we'll give you a link where you can get a certificate of attendance. Okay, Edston, handing it over to
Yeah.
you if you want to share your screen.
Yeah.
Okay, go ahead.
Okay.
There's been lots and lots of questions.
Yeah. Yeah. Are you seeing my screen, Jason?
We're seeing the web page.
A web page? Okay.
Uh-huh.
Okay. Okay. So, as Jason was talking to you, this is the interface of our software. This software can do all the different installations such as in air, buried, trough, tunnel, risers, submarine, FEM, etc. There are other modules such as the transients, the magnetic, and the crossings also. We will talk mainly about FEM, show you about FEM and what we can do in FEM. But before going into this, I would like to talk to you something about cable modeling, which is a very important a parameter in modeling any projects. Now, in our software, we could we have a library of almost 1,500 cables ranging from different voltages from 1 kilovolt up to 400 kilovolt. There are different types of cables inside each of these voltage levels. We have HVDC cables of 320 kV and 525 kV. We have all the Southwire cables pre-modeled for you. We have all the TB880 cables also. So this is a library that we provide along with the software. But if this is not required, if you have your cable data sheets, you can start modeling your software from scratch. You could add any number of custom layers. You could have pipe type cables and all those things in this. So, like a simple example to show you would be a TB880 cable. Um, One of the good cables with lots of different properties, but this is a TB880 cable. It has a corrugated sheath with also an insulation which is divided into three parts. So this some of the things that we can do in the software. You can model your custom cables from your data sheets, and you can save these cable models.
And that's the
Now,
recommended approach, right? We do provide a
yes,
data we
always.
do provide a database of pre-modeled cables. It's actually the largest of any software package. We're continually adding to that, but you should model cables, especially high voltage cables, from cable manufacturer
Cable
database.
manufacturers. Yes, so you could start from one of our cables and then build on that to get your own cables. Yeah. The next part would be to add your bonding and other settings. For example, we have um, added something that is you could have temperature restrictions to different parts of the cable. For example, the conductor, the sheath, or even the duct, the pipe, or the jacket also. So you could add that. You could add your bonding, all the types of bondings, solid, single point, or cross bonded. Um, we have a load factor calculator. If you can enter your daily loads, we could calculate load factor for you and use it for in our calculations. And once we accept this, then you would have a list of cables available for you and for which you could use in your projects here. So for this example that I'm going to show you, I'm just using the first system which I have in my database, which is the
So
K0 cable, which came
Edson,
from TB880.
so Edson,
Yeah,
I think we should explain the problem first, so that
yeah,
so the so
yeah.
for and so
Jason,
first
I
of
will.
all, you're going to show us how to model a HDD, right?
Yes, yes, that's where I'm going to next. That's where I'm going
Yeah.
to next. Yeah. Okay, uh so this K0 cable is a 132 kV 630 squared cable, and we are trying to create an installation that Jason showed in one of his slides earlier, which is three cables in three separate ducts. You have a spare duct, and then you have a casing around the ducts. So that's something that we are going to try to model, and then we could place it in different depths, and then we could find the ampacity ratings for these calculations. So I start off with this cable. This is the default arrangement you get because you wanted to arrange the cables in three separate ducts. What I could do is I could arrange them in triangular formation and then ducts to it. So I can add a duct. I could change the size of the duct looking at the SDR. For example, I can have a duct, just rough numbers. I don't have the numbers on top of my head, but just for an example, uh, I can just enter these values here. And I can assign ducts to cables. So these ducts are linked to these cables, and I have the three ducts now. Now, if I want a spare duct, I can do that also. I can add another duct.
Now
That duct would be an
the beauty about this is like this is an FEM calculation, but it's you can treat it like a normal buried installation calculation, right? And
yes,
include
you
it.
could.
It's the same cable modeling and everything that's with an FEM engine. So it's very easy to perform FEM calculations. If anyone has ever performed manual FEM calculations, you'll know that it's very, very time consuming and prone
Yes.
to a lot of errors.
Yeah, setting up the installation is the most difficult part in FEM software, but we have tried to reduce that burden from you, and we have done many things on the back end. So yeah, so we can adjust this duct position as we like. I'm just pushing it
We
down for
even
our
have a
studies.
we even have a transfer function now where you can model
Yes.
take your models from standard buried installations and transfer them into FEM, right? And vice versa.
Yes, yes, we can do the transfer as well if we have. So, and then we can try to make the casing. The casing can be as big depending on what we want. Yeah, we cannot have touching elements here. So we could have the casing. For
You can
example,
have
you
touching
can
but not overlapping, right?
not overlapping. Yes, not overlapping. So the duct materials could be specified here. For example, I could fill the duct with a solid duct filler. You could find a thermal resistivity of 1, for example. I could fill the inner ducts with water.
Mhm.
So these are the waters, and this is still with air. So these type of installations are easy to build in our software. You could add troughs or backfills, any number of backfills, any number of troughs into this arrangement. You could apply soil dry out to this, so where you could apply dry soil thermal resistivity and the temperature at which drying occurs, you can apply this to your calculations.
So that would only if the soil temperature exceeds, outside the duct to the pipe, if it exceeds the critical temperature there of whatever it is, 40 degrees,
4 degrees here,
then the
yeah.
soil will be assumed to be dried out in the FEM
Dry.
calc, right?
Yes,
Yeah.
yes, yes. The other thing is in FEM, the most important thing is how you consider the ground surface. So in IEC method, we always consider them to be isothermal. So there's no heat transfer from the earth to the air. But in IEC, but in FEM, you could consider non-isothermal heat convection models. Depending on the air temperature, the velocity of the air, etc. So you can consider them, or if you want to just go with the IEC methods, you could even consider them as isothermal. So a very powerful piece of software to use with FEM, and then you have the native soil thermal resistivity, native soil temperature. We have a calculator to find out the native soil temperature at different depths depending on the soil that you have, and you can use this for your calculations. So FEM is the only module that has a calculate button for us. All other modules are instant calculations, and because FEM is intensive calculations, we have a calculate button for it. So I will show you some pre-model exercises. So now what we're trying to see is so this type of an arrangement, if it's an HDD, we are doing it in 3 steps. The first step is it is a shallow buried step where we would assume that the bentonite has not filled the ducts properly. There are air gaps and everything. So I assume that's going to be around 1 meter from the ground surface. The next study would be putting the study a bit more deeper. For example, 5 meter just above the water table, where there is a chance of dry out occurring. The ducts would be filled with bentonite properly, but there is soil dry out. And then again, we take it further deep to around 10 meters below the water table, where there will not be any soil dry out. So these are three conditions we are trying to simulate in this software. So because we are trying 3 different conditions, we can use different tabs in
So,
our.
so it's the, hang on a
Yeah,
second. So the HDD installation, right? So I think
yeah,
what you're explaining is that we need to take cross sections at different depths, right?
yes,
So that's what you've done here. Now
yes,
we've taken what we think are the critical sections of the HDD installation. At the shallow depth, we've got a HDD section where the ducts are filled with air. They haven't been properly filled with bentonite, right?
yes, that's this one. Yeah,
Yeah, that's at shallow depth. So we're going
that's
to
shallow depth.
calculate ampacity for that situation. And then
Yes,
at 5 meters depth, which is what, just above the water table, we're going to
yes,
say that that experiences soil dry out there,
yes,
but it's bentonite filled. There is bentonite.
yes,
And then the
yes.
deepest, the deepest section of the HCD we've assumed to be 10 meters, and it's bentonite filled, but there's no soil dry out,
No soil depth.
right?
Yes,
So we're
yes,
calculating those ampacity for those 3 locations, and
yes,
would be the lowest ampacity, which would dictate the overall cable ampacity for the HCD, right?
yes, yes, yes. So yeah, so this is the shallowest portion where the ducts are assumed to be filled in air. The casing has bentonite, but the ducts have only air. So we would see that the rating for this study is around 560 amperes, 90-degree cables, 90-degree cable conductor temperature. We have used one Kelvin meter per watt as thermal resistivity and 20 degrees as the soil temperature. So 560 is the rating when it is shallow at about 1 meter. Now we take this more deeper, just above the water table. That's around 5 meters depth here. Yeah, so this is around 5 meter depth. But here, if you see that I have filled all the ducts with bentonite. All the three ducts are filled with bentonite, but I have used a soil dry out in this calculations, which is 2.5 Kelvin meter per watt drying out thermal resistivity, and 40 degrees is the temperature at which it dries out. So when you see here, the ratings have gone down from 560 amps to 445 amps, which is a considerable reduction in ampacity. And that's mainly because of the soil dry out being applied. Now, after this, we push the cable still further down below the water table where there's no soil dry out, but the depth is around 10 meters. Yeah, it's around 10 meters of depth. Yeah, let me just zoom it. Yeah, all of the conditions remaining same. Cables are arranged at 10-meter depth. Now we would see that the current rating has actually gone up from 445 to 490 amps. So the thermal bottleneck in this type of installation is where we have soil dryout being considered, which is 445 amps, the lowest of all the three installations where we have done this. So soil dryout is a very important parameter which derates a cable at least by 10 to 15% as we have seen from the previous examples. Yeah, Jason. So this is what I want to show the capabilities of our software. You
Okay.
would have all the results on the right side just to run through the results. All the results are on this side. Losses, all parameters that is calculated would be displayed on this one, including the sequence impedances and short circuit ratings, etc., etc. Yeah,
Okay,
Jason.
so we'll go to a live Q&A. I will share my screen, I guess. Yep. I will share my screen. I will also share a link in the chat where you can request a certificate, which will be sent to you in the next couple of days. Um, but Edston, I think we've answered a lot of questions.
Yeah. Yeah, I'll take some. I'll still. We can take a questions which is, I mean, which have been asked continuously, and that probably everyone else could also get an
Benefit
answer
from that.
for it,
Yeah.
right? Benefit from that. Yeah. One question was, I think we discussed it already about the maximum length that we can use for those HDDs. That what restrictions, what will restrict the maximum length?
I think I explained that,
Yeah, I
right?
explained that. Yeah,
So
yeah, yeah.
mainly the pulling tension of the cable.
Yes, yes. The other question was about longitudinal heat transfer along cables, how we can consider it in calculations.
What is it? Sorry, how can we consider?
The longitudinal heat transfer in cables.
Um, yeah, so FEM mostly.
Yeah, yeah, FEM is, yeah. Um, the other question is, can we consider other trefoils in the vicinity of other multiple circuits, right? Can
Yeah,
this
yeah,
be
yeah.
done analytically, or do we need FEM for it?
I mean, it's fine if you don't have casings or pipes, right? You can use IEC for mutual
Yeah,
heating.
yes,
But
yes,
when you have HCDs next to HCDs, you have to use FEM definitely.
yes.
How do we consider crossing for HCD and FEM? Is there any workarounds? We don't have crossings, I think.
We don't have crossings for FEM at
Workaround?
the moment.
Yeah, they're assumed to be
Yes,
uh parallel, right? So
yes,
it's like
yeah.
the worst case, the highest mutual heating.
The highest mutual
We're working on crossings for FEM.
FEM, yeah. The other question is, if water is better than bentonite, why don't we always use water? What are the problems with water filling in ducts?
Yeah, it's possible. I have heard of it. But if you want to rely on it for your entire HDD, I think they use like water vessels. So they need to contain the water, and then I assume there's expansion and contraction of the water, and topping up. The water needs to be topped up, right? So,
Yeah.
I mean, if you rely on continuous water, I wouldn't really recommend it, but I have heard of it being done.
Um, the other question is about 2K analysis, um, what we do in our software, or how we can uh, do the 2K analysis in our software.
We can do that with buried. In FEM, it's probably a little bit more manual, right?
Yeah,
Or
yeah, it is.
you would adjust the conductor current, and we know soil temperatures though, right?
Yeah, we can adjust salt temperatures. Yes, it's a
So then we can manage the the temperature of the conductor to not allow soil temperature to
so
exceed
certain levels. Yeah,
2 degrees above the ambient, right?
over them.
Within
Yeah,
within a
we
certain
can.
within a certain depth. Is
Yeah, we can show the contour. We can show the temperature rise contour,
hmm,
and then from there we can deduce what should be the current so that the temperature rise doesn't go above the 2 degree level.
hmm, hmm, hmm.
Yeah. Um, there's a question like, can we do some portion in HDD and the other normal PE ducts and run the calculation? How we can do that?
Sorry, what's the question? Sorry.
A portion of the cable in HDD and the others in normal ducts. The remaining portion normal ducts.
Uh-huh.
How can we do
Well, I
that?
mean, you can take cross sections, right? Just take cross sections and do the calculation. If it's one cable system, right, then one section will dictate the ampacity of the entire system. What do you think?
Yes.
That's
Yes, we could do sections, but still, what I think is the HDD section would be the limiting one, compared to the
yeah,
cables in
yeah,
ducts. But we
yeah,
could, as Jason told, you could have sections in our software, and you could do each section and then see which is the hottest point.
yeah, yeah, yeah.
Yeah.
Okay.
Uh, the other question, I think we'll take one more question.
Yeah.
Is it able to withdraw cables if you have bentonite filled cables?
Yeah, yeah, I think there's a simple process to remove bentonite from ducts and then
Hmm.
remove the cables.
Yeah. Yeah, I think we have taken most of the questions.
Yeah. Okay, everyone. It's been a fantastic event. Thanks a lot, Edston. Thanks everyone for attending another ELEK technical webinar. We enjoy these, and if you still have questions, feel free to reach out to our email or our live chat on our website. Also, I highly recommend that you check out our YouTube channel. We are adding lots and lots of free technical content there. ELEK Software, just look up ELEK Software on YouTube. And elec.com also has a lot of free resources. Thank you again. It's been great to produce this for everyone, and we will be doing it again and hope to see you on the next technical webinar. Thanks everyone, and good night from us.
Thank you, everyone.
See you. Thanks, guys.